Thanks, Sai. Hey, everyone. My name is Huy, and I work on the computer vision and machine learning team at Flickr. Basically, what I want to give you guys an overview of today is how we at Flickr use computer vision to better help organize and search your photos. And the key component to our computer vision systems we've found to develop over the time has been Hadoop and Storm. So I'll give you a really high-level overview of computer vision at a 10,000-foot view and dive deep down into our deployment at Hadoop and Storm. My team joined Flickr about a year ago, and at that time we were really interested in the explosion of photos that every single one of you are probably uploading to online photo services like Flickr every single day. It's been estimated that over 500 million photos are uploaded every single day, and this figure is projected to increase by twofold by the end of this year. So we wanted to figure out how can we leverage machine learning, how can we leverage computer vision to basically help you organize and search your photos. And that's really the core mission of our team. So we had this crazy idea about a year ago in saying that, what if every single photo that you upload onto Flickr, we could actually automatically apply a tag to it so that you don't have to tag those photos yourself manually. And this is a feature that we call auto tagging. And the basic idea is that you take a few photos. When you upload the photos, we run them through a barrage of classifiers. And those classifiers will produce some probability score. And if the probability is above, say, 0.95, then we say, apply the flower tag to this photo, or apply the cat tag to this photo. So now I'm going to give you a brief demo of exactly the system and how it works. So we put together just a little internal web server that we use to kind of demonstrate our technology to other groups within Yahoo. But you can see here we have a few example images. We have an area that you can drag images into. When I drag an image, it classifies that image, and here, a woman on the beach, we classify as beach. Oh, I'm sorry. So maybe I'll duck down a little bit. So here's a picture of a butterfly. We classify as insect butterfly. These green boxes basically means if you had uploaded this picture into Flickr, we would have applied the insect and butterfly tag. Now below you see we were unsure. We thought it was an animal, but we're unsure. So there's some work to be done in the future on using this only for search and not applying the tag at all. So that's our auto tagging technology, and it's all based on the pixel content. We don't use EXIF data. We don't use any other signal except the pixel content. So the tags that we apply to any given image will feed our search engine, our Flickr search engine. We recently released a mobile 3.0 app for both iOS and Android, and you can actually go and download it on the App Store right now, and we will automatically tag every single photo that you upload onto Flickr. So these are just a few examples of the classes that we can recognize. Have flower, building. These are actually some photos from my own photo album. Lots of outdoors pictures, beach, beard. You'll find that a lot in the mission. So that's our auto tagging system. Now, what I didn't mention earlier is that our team actually came in through an acquisition. And when we got to Yahoo, they had this really nice system. They gave us immediately a 90-day goal. And these were our goals. We wanted to train thousands of classifiers for Flickr. And we didn't want to do it in a piecemeal way where this wouldn't scale. We wanted to be able to train classifiers, deploy into production, and basically tag millions of uploaded photos per day and tag billions of photos in our Flickr corpus. So what I'll dive into first is our process for training, how we actually built those classifiers. And then in the second part of this talk, I'll give you an idea of how we deployed this into production. So really briefly, I want to go over some basics of computer vision. So I've had this question asked of me multiple times working at Flickr. So I wanted to really briefly just define what is a classifier. And I think for the purpose of this talk, I know my teammates are probably going to kill me for simplifying it to this level, but you can think of a classifier as just a line. And this line is special in the sense that it divides your positive training examples, these black dots here, and your negative training examples with a large margin. And when I'm talking about training a given classifier, all we're doing is we're modifying the slope of that line and the intercept of that line such that we can find the line that divides the positive and negative training examples with the largest margin. So once you have this slope and intercept, that's all you need to define a classifier. And you can then take those slope and intercept for any new training, for any new piece of data. You can run it through this line equation. We've all taken basic geometry and produce some score. If it's positive, then it's a positive example. It's classified as a dog, or it's classified as classified as not a dog. So that's the basics of what a classifier is really defined in our system. So you might be asking yourself, that's great. You just showed me how to draw a bunch of lines and dots and how to bisect these two groups of dots, right? Like how do I actually classify images? And the answer to this question is actually not too different. There's one extra pre-processing step, and this is what people in the computer vision community often call feature computation. And it's a really basic idea. You take an image, you run it through some transformation that converts it into some two-dimensional, n-dimensional point in space. And it's these points that we actually use to figure out how to find this line that divides the positive and negative training examples. So that's the basics of computer vision. You can ask my colleagues, Simon and Pierre. They've really devoted their lives to this box right here, which is, I'm sorry guys, but I mean, that's it, right? There's a lot of complexity in there. We're using some really cool tools like deep learning to figure out how do we convert an image into points that are easily separable by this line. So to summarize, image classification training is basically find a few negative examples. In our case, we generally use about 100,000 negative training examples and about 10,000 positive training examples. We name our classifier. In this case, it's a flower. And we go through these steps. For every single image, we compute features. And then we twiddle that, the slope and the intercept, W and B, to find that line. And at the end, we have a classifier. It's just defined by W and B. Now, we have to repeat this a few thousand times for every single classifier that we want to train. So this is just an example of flower, but we have thousands of classifiers in our system, so we have to repeat this 1,000 times. So this is where Hadoop comes in. It's really the key to our training system and has made training super efficient and really easy to code up, actually. We used to have a really complicated open MPI-based system that we totally transitioned over to Hadoop. So to begin with, the data in our HDFS file system is basically composed of pixel data and label data. The pixel data are these files that basically contain a photo ID and are the raw pixel data encoded in base64 format. The label data is the name of the class, the photo ID, and a true or false label for that class. So in this case here, this line is designating that photo ID 1 is a true training example for the class dog. Photo ID 1 is a false training example for cat. And I think that should be the case in most situations, unless you have cats and dogs in the same picture. So the first step in our training system is we need to combine or join this pixel data with the labels data. And we basically do it through a map and a reduce step, where we feed both the pixel data and label data directly to our mappers. And because of we take advantage of the sorting the order that is emitted to the reducer, we can basically append these photo IDs, pixel data, and a JSON list of classes and their labels. So that's the first step. What we then do is, it kind of calls back to what I was saying before. We compute features using a huge map step. And these get emitted to a whole bunch of reducers for every. So for example, for this image here, we'll emit two lines. One line will be the photo ID 1, the feature data, and then the cat and the label. And then the second line will be the same first two elements, but then the dog and the true label. And in this reduce stage, this is where we're fitting that slope and intercept to the data. And what you have coming out at the other end are thousands and thousands of classifiers. So that's our training system. All of this, these two steps are basically coordinated with each other through a Oozie workflow. We found that hand coding these mappers and reducers and coordinating all the work for them has been quite inconvenient, I would say, but with Oozie, connecting these two components has been pretty easy. So with our training system, we're able to basically boot up 10,000 mappers, about 1,000 reducers for each step, and we can train our system with thousands and thousands of classifiers in less than 6 hours. And I've said before, this replaced our open MPI system, which was a pain in the ass to me. Yeah, way faster. Yeah, way faster. We wouldn't, see, that's the good thing about Hadoop. It's a generalized framework for structuring your computation that allows us to deploy on Yahoo's cloud. And if we would have gone to our platforms team and said, hey, we want to deploy an open MPI stack, like they would have been like, no way, right? But this, just being on Hadoop gave us access to the hardware that we needed. We do it pretty often right now, every several weeks. Yeah. So there's, there's drawbacks to this system. We know the bottleneck, and if you were paying attention before, the reducers all hold in memory the pixel data, or I'm sorry, the feature data. And right now, if you expand beyond the memory capacity of a single reducer, then we can't do that. So it's a known limitation of the way that we structured our computation, but there's some promising work being done with the Valpal Wabbit team where we believe we can remove this bottleneck. So in a nutshell, that was our training system. Once we have these classifiers, how do we actually deploy a classifier into production? And this is what I'll go into right now. The production tagging system is actually broken up into two pieces. One is a batch processing system, which we use Hadoop for, and the second piece is Storm, which allows us to tag photos in near real time as you are uploading those photos to Flickr. So the batch processing system, really simple. Photos get uploaded into our web servers through a project called Fling. They get synced with HDFS. And here right now it's a manual process, but we basically kick off huge map jobs that basically take every single image in our HDFS cluster and passes it through each and every single one of our classifiers. We save this information back to HDFS, where we have what we call an indexing reducer, which is something that feeds directly to our search engine. So, this is basically how our data is structured in HDFS. It's just a huge file of photo ID and base64 encoded pixel data. And this is the actual results that we save back out. Photo ID and the JSON string representing the classes, their probabilities, and this is just repeated for billions and billions of images. So with that system, we were able to boot up 10,000 mappers, basically process the entire Flickr corpus in about a week. It turns out indexing into the search engine is a little slower, so that's actually our bottleneck right now. One of the main challenges that we had to solve for when we joined Flickr and had to deploy our auto tagging system on the Hadoop grid was, we're not Java programmers. Most of us are Python and C++ programmers. And really the Python world is really separated from Java, I would say. So we had to figure out a way to basically package our software such that we can deploy our code to a host of random machines, and we don't know what's installed on those machines, but that software had to work reliably on those unknown machines. And oftentimes we depend on really esoteric open computer vision libraries that it's going to be really hard to get an ops guy to install those on your Hadoop machines. So this was basically our solution to how to deploy our software into Hadoop Grid. There's this project called PyInstaller. And this project is, their mission is to basically, given some Python script, they're supposed to pull in all of the dependencies, all of the shared libraries, all of the Python code and libraries, and put it into basically a single file. It looked really promising. We tried it. It didn't work. So we ended up rolling our own thing. And I hate that we're rolling our own thing. I wish programming languages made it easier for you to basically package up your software such that you don't have to roll your own kind of like file system to run it. But this is what we had to do. We basically said, look, we're going to deploy a package that's just a folder that contains a lib Python 2.7 site packages, which is basically all the Python code, a bin, and an app folder. And the key here was realizing that if you build your software on a machine that has an OS older than the machine that you want to deploy on, generally your software will work, surprisingly. I didn't know this when I first started. If you copy everything in user lib and user local lib into this lib folder and basically set the LD library path when you're running your software. We got a little bit more advanced. We didn't want to copy the entire operating system into our zip file to deploy into Hadoop. So there's this neat tool, it's called strace, and it basically allows you to look at all the dependencies your software is running. So I'll give you an example of it right now. So you have your normal ls program. What are all the libraries that ls depends on? That's the question I wanted to answer. So you run strace, and you tell me every single file that ls opens, and it prints it out, which is, I mean, it's pretty amazing to me. It seems like you guys might have known this trick for many years, but yeah, so I'm telling everyone about strace. So yeah, you can see here it's opening up libsce Linux, libcap, so. I don't know what these things do, but those are the dependencies of ls when you're running it in a directory. We take that same process and we run it against our auto tagging executable, and we get this full printed list of all of our C library dependencies, and we just copy those into the lib folder, and you push that onto Hadoop, and it works. So, yeah. So that's packaging our code. It worked great with Hadoop. The next challenge that we wanted to tackle was, it's great that we can process everything in the backlog, but what about newly uploaded photos? And this was our first attempt at a system to basically tag newly uploaded photos. Again, user uploads photos into some web tier PHP code. We do an rpush onto Redis as a queue, and then some PHP workers pop those messages for the image URLs from that queue, and these PHP workers basically fork our auto tags executable. We produce some JSON output on standard out, and this PHP process saves it into our database and our search engine. Pretty simple. It worked when we first deployed it, but then something weird started happening. As we were training more and more classifiers, we noticed that the time it took to process photos was gradually increasing. And when I benchmarked it, I put instrumentation into my code, and my code said, look, the feature computation only took 300 milliseconds, and the classification only took 10 milliseconds. No matter how many classifiers I put into this auto tags executable. So it really baffled me for a long while until I realized loading that W and B matrix from disk actually took 300 milliseconds. That's 49% of the time in this setup. As you can see, like it's just forking auto tags. It's executing. It's running on one image, and it's repeating this over and over and over again. And unfortunately, we incur this model load time cost for every single image. So we looked at a few solutions. One of them was, what if there's this weird kernel trick or a kernel flag that you can set in your programs to basically memory map a piece of data into RAM and have it stay there after your executable has finished processing, has exited. So we thought, well, what if we did that and just had that classifier model sitting in memory? And then I thought better and said, this is really obscure and I don't want to introduce this into a production running system, because I think like one person in the entire Flickr team knew about this weird kernel trick. So yeah, that was a no-go when we thought about it. The next solution we were thinking about was, well, what if we could batch up a whole bunch of images and just run our auto tags binary on a batch of images instead of one by one? And that was actually a viable solution. But then you had to kind of make decisions about like how big should your batch be, and at the time, this system here was already the main system for Flickr to do these offline processing tasks, and we didn't really want to mess with this because one-by-one processing has always been like the mode of operation for this system here. So the final thing that we arrived to was, well, what if we could set up a daemon on every single one of these machines, and you could feed images into this daemon, and the daemon could produce output on some socket, and we could basically tag images through that way. Having worked on API systems before, I really don't like writing daemon code because you have to get it right and perfect so that memory leaks don't occur, or some weird input space doesn't like crash your system, and it's hard to monitor. So that's when Storm came into the picture. Sai actually suggested to me and one other team member, which was crucial in building out this system. His name is Ben. Why don't we take a look at Storm? Because it seemed like from all the information we were getting from Yahoo, the Yahoo platform team, this is the bread and butter use case for Storm. So I like to think of Storm as a partner to Hadoop. In Hadoop, you have batch processing. And in Storm, you have stream processing. So batch processing, you have finite start and end times for your jobs. With stream processing, you don't have a finite start and end time. You deploy your system, and it's supposed to run forever. Just like with Hadoop, there's a computational primitive that you structure your programs in. And that computational primitive is the map and reduce paradigm. With Storm, there's this framework that you have to adhere to when you're writing your code, and it's basically something they call a spout and bolts. So real quick, a spout is basically anything that is going to be the source of your jobs, the source of your data. So in this instance, we had Redis, the Redis queue, and we had a Redis spout, which is basically popping items from the Redis queue and emitting these job IDs downstream. And in Storm lingo, these job IDs are basically called tuples. And then to process these jobs, Storm has this thing called bolts, where basically you write a program that will accept a tuple and emit a tuple. And in this way, you can chain together spouts and tuples in what's called a topology. Here's some example code of basically setting up a topology. So that Redis thing I mentioned earlier is this image spout. It's connected to this autotags spout, autotags bolt, which is actually running our computer vision software. And it's connected also via this little call here, the shuffle grouping call, to a DB writer bolt. So this is what a topology looks like. And when you're deploying your systems, you push out topologies instead of starting up jobs. That's kind of the lingo they have. And what's nice about being able to do this is that now I can define a bolt, and I can load my classifiers once here. This is actually, real Python code that we wrote to define a Storm bolt. We can load our classifiers once, and then for every single process, or every single tuple that this bolt receives, it will just use the classifier that you loaded once to process the image. And that was the key to why we chose to adopt Storm. And let's say, I had an error in this processing code, which I never do. Let's say I had an error. Storm will take care of you. Like, if someone uploaded a corrupt JPEG image and my processing code couldn't handle it, it'll crash this bolt, but Storm will intelligently know, let's restart this guy and reprocess or go on to the next tuple. And you get this for free, which is the key here. Like, I didn't have to think about this, and that's one thing I really like about Storm. So you saw our topology. Just a few keys here. I talked about the image spout, the auto tags bolt, and then we actually have the auto tags bolt emitting tuples that are consumed by two downstream bolts. One is the search engine index writer, and then the other one is the database index writer. And this scenario is nice because let's say my auto tags bolt was the bottleneck for my Storm job. I can basically throw more machines at just this piece and not worry about having those machines work on this piece of the topology. Whereas in the previous picture, like, everything was intermingled into this PHP code. So if I wanted to increase the parallelism on my computer vision code, I would have had to increase the parallelism on my database code and the search engine indexing code. And it's really hard to make that balance. Okay, so how does everything work underneath? Like, when you define these topologies, how are they distributed? In Storm, there's basically three components. One is this thing called a Nimbus server, which is basically the master server which coordinates all of your jobs. I say that with a caveat because it's not a single point of failure, and that's the cool thing about Storm is this thing can go down and your jobs will remain running. You have a few zookeeper servers, which kind of track where your bolts are currently running. And this thing cannot go down. If this goes down, everything goes down. But the neat thing about zookeeper is that 1 out of 3 can go down and you'll be okay, or 2 of 5 can go down and you'll be okay. So that gives you pretty good high availability. And lastly, we have these things called supervisors, which are basically where all of your Storm bolts and spouts run. So you can basically just add more machines to your supervisor cluster, and your jobs will increase in speed or throughput. So I mentioned the failure modes there. You know, your supervisor nodes can go down and Storm will automatically restart those. Your Nimbus server can go down, your jobs will continue running, but you can't submit new jobs. That's the only caveat. So when you want to submit a new job, restart your Nimbus server. And zookeepers, I already mentioned that. So these are just some of the commands you can run with the Storm command line. This is the code to submit a new topology. You can list topologies currently running in your system. You can kill topologies. You can atomically deactivate your topologies. This is really cool in my opinion. Once you start building really complex topologies, you don't want to kill a single bolt prematurely and have it in this weird state where it didn't fully process, your entire job. So this command here allows you to atomically deactivate your job and to activate again. So throughout my talk, I'm sure many of you have been wondering, is Storm just another queuing system? There's many players in this space. There's Celery, Gearman, Amazon has their own stuff. And I think the answer for me is yes, but it's a lot more. I feel like the way that they've structured their code forces you to engineer your application in a way such that the scaling concerns are orthogonal to your application design. So you can design your application in this framework with spouts and bolts, and a really expert class operations team or platforms team can basically just throw more machines at it and your code magically will scale. I think it has a great deployment story. I mentioned before, you have the atomic start and stop. I mean, think about this complex workflow and trying to add atomicity to this workflow. It's not a simple task. And it's really trivial, but you don't have to write your own rsync commands anymore to push your code out into production. It just handles that for you. There's no single point of failure, and there's quite a bit of industry adoption for Storm. Crowdflower, Groupon, Facebook, Twitter, they're all using this technology to do their online processing. And amazingly, it's pretty language agnostic. We got our Python systems running in it in less than 3 weeks. So I would encourage all of you guys to try out Storm. There's a really cool project from the creator of Storm, Nathan Mars. He created this project where you can boot up a new Storm cluster in one command on EC2. And this is the project that you would use to build one of these topologies, this Storm starter project. So thank you, and that's about it. Any questions?
Just repeat the question.
Okay. Oh, yeah, sorry, I didn't mention that. So the question was, how's the speed for this compared to the previous system? We completely eliminated the model loading time, so that halved our processing time. I mean, is it speedier? No, but it's doing less work. So really big win for us. Yeah. Go ahead. Yeah, so the question is, how do you deal with failures and duplication? I didn't go into it too much in this talk, but Storm has this retry mechanism for all of its tuples. And what it does is you define your topology, and it knows all of the tasks that your tuples have to go through for it to call the job complete. If one of your tuples fails, it'll resend your message throughout the entire system, through the entire topology, sorry, and retry again. So in a sense, they call this mechanism at least once processing. So there's a potential for your jobs to, or your bolts to process the same tuple a few times. And then they have some threshold where you can say, don't try to process this anymore. Yeah. So yes, we do have data loss. You know, let me go back to the picture here. So what happens, like, for example, if my database completely goes down? Like, in this scenario, I feel like I'm hosed, right? The storm retry mechanism won't do anything for you. Like, it's not meant to handle that type of failure. It's meant to handle the intermittent, like, let's say there's a network connectivity issue here. It'll save you from those errors. But where your entire system, your DB is down, it can't do anything about that. And there's actually a project that our team is working on to build a safety net for really catastrophic events. And we're actually going to use Hadoop and Uzi as like a safety net for Storm. Oh, okay, go ahead. Yeah, we'll see. It depends. I can't say anything right now, but I'm sure there's some piece of our code that aren't competitive advantages that we'll be able to push out. So, go ahead. Oh, wait. I think you were first, and then we'll get you. Okay.
Your Redis queue, is this only in memory, or do you have some persistence? Like, let's say in the case where the database at the end fails, like, how long can your system survive without dropping data?
So the Redis queue, we have a high availability setup. I wasn't personally involved in the high availability structure for it, but our system can build up for I think 4 days before it blows up. So,
I can talk a little bit about that. The guy who worked on it unfortunately couldn't make it today. It's a good question. We do rely on in-memory store right now. It is not a persistent store. We don't use it as a persistent store. We use it as a simple queuing system. We do have plans to migrate. Again, end-to-end, this took us about 6 weeks to completion, or less probably. So I would say we're in the first version of our iteration to get completely stormized. So we don't have persistence in front. We would like to have persistence in the front. We are actually going to move to either RabbitMQ or some other messaging system for it, for multiple reasons. One of them being that Redis doesn't natively support SSL. For Yahoo, even intra-colo traffic is all SSL, so we want to move to that. So, but this is a easy point of entry for us, so we used Redis. over time we will productionize it more.
Yeah. Mm-hmm. Okay, so the question was, how do we handle our dependencies when we're using Python, I guess, right? So this is one of the great things about Storm. We actually just took the package we built for Hadoop, dropped it in Storm, and it worked. So S-trace mechanism and that package structure. I really wish dependency management was more well structured. I feel like the Go programming language does a really good job of packaging everything into a single binary that you can push anywhere that's portable. But yeah, that's what we had to do for Python. Yeah. 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 Anything else? Mm-hmm. So is the question is like how accurate is our classifiers, or I would say our classifiers are pretty accurate. Can't get there. So I want to say when we make a guess, we're pretty sure we're going to be right, but we don't guess often. So it's higher precision, a little bit lower recall, and it's some of the work that our team is doing is always trying to push this boundary to get both higher precision and better recall. So we'll make mistakes. Could you repeat your question? Mm-hmm. Yeah, yeah. Okay. So the question is, how do we think of new classifiers to add to our system? And I don't know if I can go into too much detail about our process, but a little bit of it is we think of new classifiers to train, and we find those images and positive, negative training examples, and add new classifiers. I think that's as much as I can say. Yeah. Yeah. Like user feedback. And, yeah. In the back. Wait, what? Oh.
We look a lot at the corpus of images on Flickr, the things that people tag frequently, the things that people search for frequently, and we look at like where in that data set. Sorry, didn't mean to hijack. So we look a lot at the corpus of images on Flickr, and we look at the places where what do people tag frequently in their images? I'm not going to start over a third time. Yeah, sorry. Hey, I'm Andrew. I'm the product manager that works with Huy and the vision team at Flickr. So we look at the images that we have. We look at what do people tag frequently, what do people search for frequently, and where do we have the availability of a good data set that we can use to train a classifier. So we need a good positive set of images that matches to something that we want a classifier for based on various proxies for user demand for those tags and search terms. Then based on that, we've created a classifier, and Huy and the team have created an amazing editorial tool that allows us to sort of very quickly review the classifier, figure out if the quality is up to par, and if it's good enough, then we'll roll that to production, and if not, we'll hold it back until it's ready.
In the back? We have a few internally. We have thousands of classifiers. They're applied across all images. Oh, will we typically tag an image, you say? Okay, I see, I see. So the question was, for any given image, how many classifiers will fire on that image? And I haven't done too many quantitative studies on this, but like 3, usually 3. Mm-hmm. We don't have that problem right now. Yeah. Do you want to follow up on that, or you or Jerry? Yeah. Yeah. Animated GIFs. Jerry just tried our system on some video. Do you want to speak to that?
Yeah, so we just ran a really simple, sorry. So I'm Jerry, and I work also in the vision group. So we just ran a simple test using the same system on video. And we did it very simply just by parsing the video into keyframes and running those through Storm. And it worked well. I mean, we like initially we see some challenges in getting good frames with reduced motion blur and things like that. But the same system can handle video. And at some point we'll also be auto-tagging videos for sure.
Cool. How are we doing on time? Or good? Okay. So. Oh, the negative training examples. Yeah, I think it's generally easier to find a lot of negative training examples than to. It's a little bit more expensive to get the positive training examples, and we need to do a more quantitative study. But this is our first initial pass at the system. If we have a different ratio of positive or training, it hasn't seemed to affect the system that we've created so far. Yeah. So one more question, and was there someone over here, or? Go ahead.
So I'm going to change a bit to some of the other things, but if you feed your model for the positive examples, you feed them from user tag photos, and if you do you have any way of identifying who just tag that user photos versus good?
So right now we've built our own data sets, but we want to look at this problem of maybe using user tags in the future. But it's been sufficient so far from the data sets that we built. Yeah. Okay, so thanks everyone. Yeah.
All right. Thanks, Huy.